I have opened the Machine IBR workspace in PSCAD here. You can see this directory is temp i2x PSCAD machine IBR.pswx. When I go to the solar circuit project, the references got broken. So if this happens to you, right click on it and do switch reference, and it is going to pick up this local copy of a solar with the power plant controller, and then this other one. Oh, this is the power plant controller. I'm going to right click, switch the reference, and it'll pick up this little power plant controller. So if I save, I hit Control S there, then it should be good to go. This is basically the same circuit that you used on August 3rd. One thing we're going to change, as I mentioned in the introductory presentation, the resistance of the step-up transformer. I'm going to double-click on that, and the reactance is 0.12 per unit, but the copper losses I want to change that to 0.01, so we get 1% resistance. You can see that there. It's a small change, it's not going to make much difference. We have the three-phase fault at the point of connection, and so with the reactance, the inductance of 0.025 henries, that should give us 50% retained voltage. It is a three-phase to ground fault. If you want to experiment with this, you can click on the resistance symbol there, and you can go to the fault type. You can make it a single line to ground fault or line to line fault, whichever you like. Another thing that has changed or expanded is the COMTRADE setup. So I'm using 10 channels, A1 through A10. There are 10 data nodes wired up to those. Describe what the channels are in the introductory video. We're recording between 4 seconds and 10 seconds, so the simulation is going to run for 10 seconds. We don't care about the first 4 seconds. We're letting the controls stabilize before the event occurs. The fault's going to happen at 5 seconds. Now double click on the symbol. So you notice we have a couple of choices for the COMTRADE standard, 1991 or the 1999 version. Using the 1999 version, that is fine, that is plenty for us. We don't really have to change too much here. The analog output maximum is 4096, so I think that's kind of 12-bit resolution. The choices we have here are 91 or 99. Each of the channels, I overwrote changed the default names. By default, PSCAD will call these by A1 and then space, and then whatever you type in. But since I want the names to match the post-processing script, I'm going to name them, VA. This one is going to be IA. The phase can be entered if it's appropriate. And that's about all we need to worry about here. I encourage you to read the help and also read the standard itself if you haven't already. But we're going to be able to use this setup for most of the simulations that we run. We're monitoring the quantities of interest for evaluating the model or the plant performance, and if we need to, we can add more channels later. We might want to example, add some digital channels if there's some trip signals coming out of the plant. But we'll do that later. This simulation is running at a 10 microsecond time step. It's a switching level model. The inverter, if you remember, the plot channel is every 100 microseconds. But actually, here, you can have a sampling rate that's different. So we're recording every 5th time step for every 50 microseconds. We should not record faster than the underlying simulation time. This is ready to go. So I'm going to start the simulation. And this is going to take a while, so I will pause the video while it is running. The simulation is finished, and you can look around on the graphs that appear on the screen, and it should look familiar from August 3rd. In this case, it's the same. I'm going to bring up the Windows Explorer so we can see where the COMTRADE files ended up. I've highlighted the workspace that I opened. When I ran the simulation, it created this temporary directory. Yours should look similar. It should start with Solar 2. But I'm using the Intel Fortran compiler, so mine starts with I have a .if18_x86. You may have something different if you're using the GNU Fortran compiler. But if you go under rank 4 zeros into 1, then run 4 zeros into 1, these are where the COMTRADE files are. We don't worry too much about the header file, but the channels are configured in the CFG file, and then the integer data, it's just an ASCII file, is in this .dat file, so we'll need to know where those are. And I would encourage you to open those in a text editor, see what's in there, compare it to what's in the standard, if you have time. So now we're going to go over and look at a similar test setup with a synchronous machine. And this is the same grid, similar step-up transformer, three-phase to ground fault, the same COMTRADE setup. I've not attached an exciter or a governor to the machine. We may do that later. I'm going to double check this transformer to see that I remember to put in positive sequence inductance 0.12, and here's my copper losses, so I'll do it for that. The machine itself, so let's look at that. On the basic data, this is where you put in the rating, so it's going to be 100 MVA. The inertia constant is 3 seconds. Most of these can be left at the default. Under generated data format, copied this from the first benchmark case for subsynchronous resonances using that commonly used stability data format with the time constants and reactances. The initial conditions, this is where I put in the angle that I estimated from the introductory video, considering the source reactance and the generated step-up reactance. What angle should I have approximately to get the machine initialized the way I want? So you fill this out, probably what you're used to doing for a positive sequence dynamic stability program. This simulation should run a lot faster. I ran a simulation time step of 50 microseconds. This is okay for a synchronous machine. There's no rapid switching or anything going on. It should be ready to go. I will run it. And I don't know that I will bother to pause the video this time. Let's see how it's doing. There it goes. Took a while to start up, but it has finished. So you can look at, need to reset the extents on some of those. We can see the speed oscillating for the machine, and also you can see the angle. You're going to see, if you played around with some of the parameters, this can easily go unstable. The fault is fairly severe because there's no parallel paths around it. And let me see if we'll see it better in the COMTRADE. The behavior of the terminal currents is pretty interesting. If you don't have enough resistance in the circuit, you have enough DC offset that you can miss some of the current zeros. Bring up the Windows Explorer, and I have a machine 2 IF18 directory where my temporary results are stored, and I've got a COMTRADE file for the machine simulation. It should be about the same size because I'm measuring 10 channels at the same sampling time step for COMTRADE. Actually, one thing I may have forgotten to show. Is the output file name. You can actually specify that here like a root file name. So this is where the machine came from. I typed something in called solar for the solar 2 case. And you can also have this set up to, if you're doing multiple runs, to have it auto increment some of the names and numbers in the file names. That's all we need to do for now. We generated 2 simulation cases to compare the results for. I'm going to bring up the Windows Explorer again, and we can go to the Python directory. And if you remember, in August 3rd, we started up by double-clicking on notebook.bat. I have a notebook2.bat for this session, and it is going to start up this Jupyter workbook. So I'm going to double-click on that, and you see the server coming in the background, and my browser started and brought it up to that workbook. So there's several cells here. The first one, I'm just going to run this. What that does is import the packages we need, define some per unit bases. This is a utility function to load the channels from COMTRADE, and so we haven't actually done any work yet. So and I'm going to use matplotlib to do the plotting. So this again just defines some of the support functions. So I imported matplotlib, and then these are some utility routines that are going to plot different cases on top of each other. If this doesn't work that well for you, if you can do matplotlib, you can try and this comment isn't relevant anymore. I can get rid of that. But if matplotlib notebook doesn't work for you, you can try matplotlib inline or matplotlib widget. Some of those enable the zoom in the browser better than others. We don't really need the zoom for this case. But what I'm going to do now is run this next cell, set the session path to match the location of your unzipped sample cases. So this happens to match where I unzip the files. And so this should run. I'm going to click run. And what should happen is it read two files. It read the IBR one first, and then it read the machine one. And you get some summary of the channels that it found and the scaling factor. So in this case, the scaling factor is going to be 1, because the the voltages are going to be in kV, the current in Ka. P and Q are going to be megawatts and megabars respectively. You probably have to change this part of the name. I don't remember what it's called. It maybe start with GF something, for the GNU Fortran. But if you don't have this matching correctly, then you would get an error instead of this output. We're going to skip over this. You folks are not using the EMTP. But I'm going to run these 5 plots in a row. And this first one plots the IBR voltages and currents. And you see that the current goes up, the voltage drops, the RMS voltages drops from 1 to 0.5 per unit. P and Q respond as appropriate, and then you see the frequency is deviating by 1/4 of a hertz. That's maybe just a measurement artifact, because it's measured at the point of connection where it's connected to a strong grid source. Okay, the next one I'm going to do is show a case plot for the machine. And so this is not comparing apples and apples at all. But look at the currents. So the currents increase quite a bit, as you would expect for a machine-fed fault. There are no, if we zoomed in, you would see that none of the current zeros are missed. But if I were to reduce that resistance in the step-up transformer, the DC offset persists faster than the AC offset, and so you will see actually this current's not going through 0 for some time. And the system is almost ready to go unstable, but the voltage drops to 0.5 per unit during the time of the fault. The frequency responds similarly, even though it's a synchronous machine. You do see some evidence of swings. We're not plotting all 6 seconds of the simulation here. But the value of COMTRADE, and you can do this in PSCAD as well, but what we're going to be able to do is really automate the post-processing using this Python post-processing facility. We're just comparing the machine and the IBR behaviors. So I plotted the voltage in RMS, the real and reactive power, and the frequency. And these other 2 plots, click on those to see what they happen, what they do. I'll just click on one. But you're getting each channel individually this way, each voltage separately, each current. P, Q, and the frequency. So that's all we need to do for now. I just want to make sure that you can get this working, for yourselves. Actually run a case, get the COMTRADE data plotted. I know we didn't do COMTRADE plotting in the hands-on session during August 3rd, so we'll be making use of this a lot going